Hello there, and welcome to the Sleepy Science Channel. I'm so glad you're here. Maybe it's been a long day. Or maybe you're the kind of person who likes to fall asleep wondering what lies beneath your feet, beneath the forests and fields, beneath the oceans and mountains, deep into the heart of the earth itself. Either way, tonight's journey is for you. You don't need to do anything now but rest. Let your breath slow, your thoughts soften, and your body grow heavy, as if gravity itself is pulling you gently downward through layers of stone and time. Because tonight, we're going to take a quiet, thoughtful journey all the way to the center of the earth. We'll begin at the surface, where life unfolds in the daylight, and then we'll drift inward through the Earth's crust, down into the deep mantle, and finally into the ancient core, where molten iron moves like water and the planet's magnetic heartbeat begins. We'll go slowly, gently, just one quiet layer at a time. And just before we begin, if these calm explorations bring you rest or offer a soft place to end your day, consider tapping the like button and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. Picture yourself standing barefoot on the ground. The surface is cool beneath your feet. Maybe it's the packed earth of a forest trail or the smooth stone of a mountain ledge. The air is still. The stars above are distant and quiet. And below you, the earth stretches downward, far deeper than your eyes can see. Now, imagine beginning to sink. Not suddenly, but slowly, gently, as if the earth were welcoming you in. You drift downward through topsoil and tree roots, past glinting minerals and sedimentary layers. A pale fossil passes beside you, the imprint of a leaf held in stone. Then it's gone, and you're still sinking. Beneath the world we know lies a planet within a planet. Our Earth is layered, like a story told in chapters of pressure and heat. The crust is just the beginning, a thin, rocky skin that floats atop something far more vast and ancient. Below that is the mantle, a dense, slow-moving ocean of solid rock that flows over time. And at the center lies the core, a hidden realm of molten iron and crushing pressure, where temperatures rival the surface of the sun. We've never seen these inner regions directly. No camera has filmed them. No human has touched them. The deepest hole we've ever dug only reached the crust, just over 7 miles down. But the Earth is more than 4,000 miles deep. Everything we know beyond that comes from the echoes of earthquakes, from waves rippling through stone, and from the shifting patterns of the magnetic field that shields our world. And yet, from these faint clues, a picture emerges, one of heat, movement, and transformation. Deep inside, the Earth is alive with motion. Rock flows, metal spins, heat rises, and slowly, this internal dance reshapes the surface of our world. Mountains rise, oceans open, continents drift, all because of the forces hidden below. So as we begin our descent, you might wonder, what exactly lies beneath us? What ancient processes stir in the dark? How does a planet stay warm for billions of years? And why does the deep interior, a place we can never visit, hold so much power over the surface we call home? These are the mysteries we'll explore tonight. Quietly, gently, one layer at a time. Let's begin where we live, on the crust. The outermost layer of the Earth, and the only one we've ever walked upon. It may feel solid and eternal beneath our feet, but the crust is thinner than we often imagine. If the Earth were an apple, the crust would be the skin, just a fragile boundary atop a vast interior world. And this thin shell, is not the same everywhere. It comes in two main types: continental crust and oceanic crust. Continental crust is what forms the land masses we live on. It's relatively thick, averaging about 20 to 40 miles deep, and made mostly of lighter granitic rocks like quartz and feldspar. Beneath the oceans, however, the crust is quite different. Oceanic crust is denser and much thinner, only about 3 to 6 miles deep, and made primarily of dark volcanic rocks like basalt. This difference in density is one of the reasons continents float higher than the ocean floor. The crust isn't just resting on solid ground. It's floating, slowly, imperceptibly, atop the soft, semi-fluid mantle below. And these floating plates of crust aren't fixed in place. They drift. They collide. They break and reform. This is the foundation of plate tectonics, the theory that explains the movement of Earth's outer shell. The crust is broken into large sections called tectonic plates, which slide across the mantle like puzzle pieces adrift on a sea of rock. These plates are in constant slow motion, moving only a few inches per year, but over millions of years, their movements shape the entire surface of the planet. When two plates move apart, magma from below rises to fill the gap, forming new crust at mid-ocean ridges. This is happening right now, beneath the Atlantic Ocean, where the Eurasian and North American plates are drifting apart, widening the ocean basin bit by bit. When plates move toward one another, the result can be far more dramatic. In some places, one plate is forced beneath another in a process called subduction. As it sinks into the mantle, the descending plate melts and fuels volcanic activity. This is why volcanic arcs, like those that form the Pacific Ring of Fire, often trace the edges of subduction zones. In other regions, plates grind past each other sideways. These are transform boundaries, like California's San Andreas Fault. Here, the movement is not smooth, but jerky. Stress builds up until it's suddenly released, and when that happens, the ground shakes. This is the mechanism behind many of Earth's earthquakes. So while the crust may seem quiet from above, it is anything but still. It is a shell in motion, fractured and reshaped by the slow churn of forces beneath. Mountains rise where plates collide, like the Himalayas, still growing as the Indian plate pushes north into Asia. Volcanoes erupt along rifts and subduction zones, sending magma and ash into the sky. And earthquakes mark the fracture lines where the stress of movement finally breaks free. This restless surface has shaped not only the landscape, but the history of life itself. The drifting of continents changes ocean currents and climate. It opens and closes migration routes. It brings species into contact or seals them off in isolation. Over geologic time, the crust has written the story of evolution in rock and reef, in rift and ridge. And yet, the crust is only the beginning. Beneath it lies a deeper engine, the mantle, that drives this movement forward. The crust is the outermost shell, but the heart of the Earth's motion lies deeper still. If you were to hold a small piece of the Earth's crust in your hand, a chunk of granite from a mountain, or a slice of basalt from the ocean floor, you'd be holding a record of Earth's formation, chemistry, and motion. The crust is made of rocks, and those rocks are made of minerals, arranged in intricate crystal patterns, formed under pressure, heat, and time. The most abundant elements in the crust are oxygen and silicon, which together form silicate minerals, the backbone of Earth's rocks. Quartz, feldspar, mica, and amphibole are all silicates, and they make up the bulk of continental crust. These light-colored, lower-density minerals are the reason why continents ride higher atop the mantle than oceanic plates. In contrast, The oceanic crust is rich in denser iron and magnesium-bearing minerals like pyroxene and olivine, which contribute to the dark hue of basalt and gabbro. Granite, with its large crystals and varied mineral content, dominates the continents. Basalt, thin-grained and dark, covers the ocean floors. Limestone and sandstone, formed from the accumulation of biological and sedimentary debris, add to the diversity, especially in shallow marine environments. And scattered throughout are pockets of rare minerals, gems, ores, and elements that have been concentrated by geological processes over millions of years. These are the veins of copper, the seams of gold, the deep pockets of lithium and rare earths that modern technology depends on. But while the surface rocks are accessible, much of the crust lies out of reach. To understand what lies deeper, scientists have had to get creative. Drilling projects offer the most direct path downward, though even our most ambitious attempts have barely scratched the surface. The deepest hole ever drilled, the Kola super-deep borehole in Russia, reached just over 7 miles into the crust after decades of effort. Temperatures and pressures became so intense that deeper progress proved impossible. And yet, that narrow tunnel offered a glimpse into rocks more than 2 billion years old, formed long before the first complex life. To go deeper still, scientists rely on indirect methods, most notably the study of seismic waves. When an earthquake occurs, it sends out ripples through the earth. These waves travel at different speeds depending on the density and composition of the materials they pass through. Some waves can travel through liquid, others cannot. Some bend and refract, others bounce. By placing sensitive instruments called seismometers around the world, geologists can track how these waves move and use that data to infer the structure and composition of the crust and layers below. Seismic tomography, much like a CT scan of the Earth, allows scientists to build three-dimensional maps of crustal thickness, faults, and subduction zones. These images reveal the boundaries of tectonic plates, the presence of buried mountain roots, and the slow, creeping movements of rocks many miles below the surface. With enough data, we can even see rising plumes of hotter mantle rock that may someday form new volcanic islands. Other tools help as well. Gravimetry measures variations in the pull of gravity caused by denser or lighter rocks underground. Magnetometers track the subtle changes in Earth's magnetic field caused by buried mineral deposits. And satellite imagery reveals surface deformations and uplift that hint at forces building from below. Together, these methods form a layered understanding of a world we cannot directly reach. We map the crust not with our hands, but with echoes, fields, and data, slowly building a picture of the Earth's restless skin. And yet, the crust is not a boundary. It is a gateway. Everything above us, every tree, every mountain, every ocean wave, is shaped by what happens below. The crust is where geology meets biology, where deep Earth processes find expression in the landscapes we know. The crust may seem like a thin outer shell, but for life on Earth, it is everything. It is the stage on which biology unfolds, the surface that plants root into, the source of every element our bodies require, and the protective boundary that shelters us from the volatile forces of the deep. Without the crust, there would be no continents, no stable climate, no soil to nourish forests, and no shelter from the heat that simmers far below. In its uppermost layers, the crust weathers slowly over time, broken down by wind, rain, and ice. This weathering releases minerals that flow into rivers, accumulate in soils, and provide nutrients for plants and animals. Calcium, potassium, iron, phosphorus, all essential to life, come from the slow erosion of rocks. Even the carbon cycle, which regulates the planet's temperature over geologic time, is tightly connected to the crust. Carbon dioxide from the atmosphere dissolves into rainwater, forms weak carbonic acid, and weathers silicate rocks. The resulting minerals carry carbon into the ocean, where it eventually becomes part of limestone and other sediments. Over millions of years, plate tectonics lifts these sediments back up as new mountains, returning stored carbon to the atmosphere through volcanic eruptions. It's a long, slow cycle, but one that keeps the planet stable enough for life to thrive. Without the constant renewal and recycling of crustal material, Earth's atmosphere and oceans would become hostile and unbalanced. The crust also gives rise to the landforms that shape ecosystems and climate. Mountain ranges influence rainfall and temperature. Ocean basins control the circulation of currents. Ridges, valleys, and volcanic islands create unique niches for life to evolve. Biodiversity flourishes in the cracks, edges, and margins of this dynamic shell, a direct consequence of the crust's uneven, shifting nature. But even as we focus on the crust, we must look deeper to understand why it behaves the way it does. The crust does not move on its own. Its restlessness is powered from below by heat rising from the mantle and by even deeper forces at the planet's core. And one of the most profound links between the crust and Earth's interior lies not in rock or heat, but in something invisible, the magnetic field. Earth's magnetic field is generated in the outer core, where molten iron and nickel swirl in complex currents. This geodynamo effect produces a protective bubble, the magnetosphere, that surrounds the planet and shields it from the solar wind. Without it, high-energy particles from the Sun would gradually strip away our atmosphere, just as they did on Mars. Life on the surface, especially early life, may not have survived without this invisible barrier. And yet, the crust plays a key role in how we understand the field. As lava cools and solidifies at the surface, iron-bearing minerals within it align with the direction of Earth's magnetic field. These tiny compass needles become locked in place, recording the field's strength and orientation at the moment the rock formed. Over time, as tectonic plates carry these rocks away from spreading centers, we can read the magnetic patterns they leave behind, like lines in a book that tell the history of Earth's magnetic reversals. Some crustal rocks are magnetized so strongly that they form local magnetic anomalies, subtle deviations that reveal both the field's ancient behavior and the movement of plates over hundreds of millions of years. So in this way, the crust is not just the outer shell, it is a living archive. It holds the story of deep time, of shifting continents, of ancient climates, and of a planet constantly shaped by what lies beneath. The crust supports life, preserves its history, and bears the imprint of the fiery heart hidden far below. And as we leave the crust behind, we descend now into that deeper world, to the vast flowing mantle, where stone behaves like liquid and the engine of the earth begins to turn. If you've ever stood atop a mountain ridge, felt the tremble of an earthquake beneath your feet, or seen the steam rise from a hot spring, you've witnessed the outer echoes of Earth's inner workings. The crust may seem like a stable stage, but it is in constant dialogue with the deeper layers of the planet. Mountain ranges form where crust is forced upward, the result of plates grinding slowly together. Beneath the Himalayas, the Indian plate presses into the Eurasian plate with unrelenting force, creating not only soaring peaks, but deep roots that extend far into the mantle. These roots are made of dense rock, pushed downward by the same collision that lifts the mountain skyward, a mirror image of the surface, buried in darkness. Volcanoes also offer a direct connection to the mantle below. At rift zones and subduction boundaries, magma rises through cracks in the crust, bringing with it the chemistry and heat of the deep earth. Each eruption paints the surface with material from miles below, forming islands, altering landscapes, and sometimes shaping entire climates. Even the gentle steaming of a geothermal spring whispers of a hidden world, of mantle heat warming water beneath our feet, rising through fractures in stone. Surface phenomena are not isolated events. They are messages, signs of slow, powerful processes far beneath the visible world. Earthquakes record the release of stress built up over decades. Uplifted plateaus and folded rocks speak of crust buckling under deep pressure. Every hill, basin, rift and reef has been shaped not just by weather and time, but by the movement of stone deep inside the earth. The crust is the surface of the story, but to understand the full tale, we must go deeper. And so now, we leave the outer shell behind and begin our descent into the mantle. Beneath the crust lies the mantle, a vast, powerful realm of rock so deep and dense that it holds most of the planet's volume. It stretches from just below the crust to nearly halfway to the Earth's center, beginning around 20 miles down beneath continents and continuing for more than 1,800 miles beneath our feet. But the mantle is not uniform. It is divided into two major zones, the upper mantle and the lower mantle, separated not by a sharp line, but by gradual changes in pressure, temperature, and the behavior of rock. The upper mantle, closest to the crust, is the most dynamic. This is where slow, creeping convection currents rise and fall, transporting heat from the deep earth upward and moving the tectonic plates at the surface. While the rock here is technically solid, it behaves like a very slow-flowing fluid. Over long spans of time, it bends and deforms, creating the movement that drives earthquakes, mountain formation, and volcanic activity. Beneath that lies the transition zone, a region from about 200 to 400 miles deep, where minerals change form under extreme pressure. Olivine, a common upper mantle mineral, transforms into new, denser crystal structures. These changes slow the movement of material and affect how seismic waves travel, allowing geologists to map this boundary from afar. Deeper still is the lower mantle, a zone of immense pressure where rock is hotter, denser, and more rigid. Though it moves more slowly than the upper mantle, it still flows, carrying heat from the core toward the surface. This slow circulation of solid rock, known as mantle convection, is what keeps the Earth geologically active. Without it, the crust would fall silent, the plates would stop drifting, and the surface would freeze in place. Though we often think of the mantle as solid, over long spans of time it flows, slowly but continuously. This creeping motion is driven by heat, and it is the deep engine that powers the shifting of continents, the birth of new ocean crust, and the rise of great mountain ranges. The surface of the Earth may move just inches per year, but those movements are the result of immense forces rising from below, the mantle's steady convection currents. Mantle convection is much like the boiling of a thick, heavy soup, slow, deliberate, and constant. Near the core, rock is heated to extreme temperatures, becoming slightly less dense. This buoyant material rises toward the surface. As it travels upward, it cools, spreads laterally beneath the crust, and eventually sinks back down in cooler regions. These massive cycles of rising and sinking rock act like a conveyor belt beneath the tectonic plates. The plates themselves ride atop these currents, moving as the mantle flows beneath them. Where mantle material rises, we often find mid-ocean ridges, long underwater mountain chains where plates are being pushed apart and new crust is formed. Where it sinks, we find subduction zones, where one plate is dragged beneath another and returned to the deep earth. Even areas of seemingly quiet interior land can be influenced by this slow mantle movement, lifting or stretching the crust over millions of years. But what gives the mantle the heat it needs to move at all? Some of the heat inside the Earth is primordial, left over from the planet's violent birth more than 4.5 billion years ago. As particles collided and merged in the early solar system, they released vast amounts of energy. That heat has been slowly leaking away ever since, through the crust and into space. Yet if Earth had only that original heat, it would have cooled and fallen silent long ago. What keeps the interior warm today is another, quieter process: radioactive decay. Certain elements found in Earth's rocks, including uranium, thorium, and potassium, are naturally unstable. Over time, their atoms break down into more stable forms, releasing heat in the process. This decay happens at a steady, predictable rate, and the energy it produces is immense. Though each atom releases only a tiny amount of heat, the Earth contains so many radioactive isotopes that together they contribute a significant portion of the mantle's warmth. Most of this radioactive material is found in the crust and upper mantle, where it continues to heat the surrounding rock. That heat then rises, driving convection in the deeper layers. In this way, radioactive decay acts like a long-burning fire deep within the Earth, a steady, patient source of energy that has powered the planet's interior for billions of years. It is this combination, leftover primordial heat and ongoing radioactive decay, that keeps the mantle active. Without it, the rock would grow still. The convection would stop. The plates above would cease to move. There would be no new mountains, no fresh volcanic islands, no renewal of the crust. The very face of the Earth would change, not overnight, but slowly, as the inner fire went out. But as long as these heat sources remain, the mantle will continue to flow, slowly, powerfully, and invisibly, shaping the world above. Not all heat in the mantle rises as smooth, symmetrical convection cells. In some places, narrow columns of exceptionally hot material push directly upward from deep within the mantle, possibly from the boundary between the mantle and the core itself. These are known as mantle plumes, and where they reach the base of the crust, they can create persistent volcanic activity for millions of years. One of the most well-studied examples of a mantle plume lies beneath the Pacific Ocean, the volcanic chain that formed the Hawaiian Islands. Unlike most volcanoes, which are found at the edges of tectonic plates, the Hawaiian Islands lie in the middle of the Pacific Plate. They were not created by plate collisions or subduction zones, but by a stationary plume of hot mantle rock rising beneath the moving plate. As the Pacific Plate drifts northwest over the mantle plume, the plume punches through the crust, forming one volcanic island after another. The Big Island of Hawaii is the youngest, currently sitting directly above the hotspot. Older islands like Maui and Oahu were once above it, but have since drifted away and become volcanically quiet. Even farther northwest are seamounts, ancient volcanoes now submerged below the waves, marking the slow trail of the plate over the stationary plume. This volcanic breadcrumb trail offers powerful evidence of both plate motion and mantle behavior. It tells us that the mantle is not homogeneous, but contains focused upwellings of hot material that can last for tens of millions of years. Some scientists even believe these plumes may begin near the core mantle boundary, rising more than 1,800 miles through solid rock before reaching the surface. But how do we know what's happening so deep below, especially in a place we can never reach? The answer lies in one of the Earth scientists' most sensitive tools: seismic waves. When an earthquake occurs, it sends vibrations outward in all directions, like ripples on a pond, but moving through solid rock. These waves travel at different speeds depending on the temperature, density, and composition of the material they pass through. By studying how these waves move, bend, reflect, and change speed, scientists can infer what the deep Earth is made of. There are two main types of seismic waves: PW waves, primary or pressure waves, and swaves, secondary or shear waves. P waves travel through solids, liquids, and gases, and are the fastest seismic waves. Swaves, however, can only travel through solid material. When an earthquake sends waves through the Earth, scientists can detect where swaves disappear, revealing areas of molten rock or liquid metal. In the case of mantle plumes, seismic waves slow down as they pass through the hot, rising material. This creates what scientists call a low-velocity zone, a region where seismic waves are delayed due to higher temperatures or partial melting. By mapping these slow zones beneath known hotspots, researchers can trace the vertical shape and depth of mantle plumes. Using a technique called seismic tomography, scientists combine data from hundreds or thousands of seismic stations to build a three-dimensional image of the mantle. These images show variations in wave speed, like seeing the Earth's interior in soft shades of hot and cold. The Hawaiian plume, the African superplume, and other features have all been revealed through this technique. Through these distant vibrations, we begin to see what would otherwise remain invisible: narrow rivers of hot rock rising through a planet of stone. Mantle plumes connect the deepest layers of the Earth to the surface, and seismic waves are the echoes that tell their story. The idea that rock can flow might sound contradictory at first. After all, we think of stone as hard, rigid, and unchanging. But in the mantle, under immense pressure and heat, solid rock behaves in a way that defies our everyday experience. It doesn't melt into a liquid, but it does move, stretching, bending, and deforming with a kind of slow grace that only becomes apparent across vast spans of time. This is called viscous flow, movement that happens not because the material is liquid, but because it's under such intense heat and pressure that it behaves more like a thick, sluggish syrup than a brittle solid. The rock doesn't crack or shatter. Instead, it slowly changes shape as it flows in convection currents deep beneath the surface. Even at temperatures of over 2,000 degrees Fahrenheit and pressures that would crush steel, the mantle remains solid, yet it moves. This strange, in-between behavior is part of what makes the mantle so important in Earth's long-term evolution. Its flow isn't visible to the eye, but it's measurable. Over time, it carries heat from the deep interior up toward the crust, and it transports cooler material from the surface down toward the core. These slow, circulating currents drive everything from the drift of continents to the birth of volcanoes. And the consequences of that movement ripple upward, affecting the crust, the oceans, and even the atmosphere. The influence of the mantle on surface geology is vast. Wherever hot mantle rises, it pushes upward on the crust, creating bulges in the surface that can lead to the formation of plateaus, rift valleys, or volcanic fields. The East African Rift, for example, is a place where the crust is being pulled apart by an upwelling of mantle material, creating deep valleys and scattered volcanoes across the region. This process, happening slowly over millions of years, is literally tearing a continent in two. Volcanic activity is one of the most visible outcomes of mantle behavior. Where hot plumes rise from deep below, they melt portions of the upper mantle, generating magma. This molten rock, buoyant and hot, makes its way through weaknesses in the crust until it erupts at the surface. Over time, repeated eruptions build up volcanoes, towering landforms that can stretch miles into the sky and influence regional climate, ecosystems, and even the evolution of life. Different types of mantle material produce different styles of volcanism. Hot, low-viscosity magma tends to create broad, gentle shield volcanoes like those in Hawaii. Cooler, more silica-rich magma leads to explosive eruptions like those seen in the Pacific Northwest or at Mount Vesuvius. These differences are not random. They reflect variations in mantle chemistry and temperature that have built up over geologic time. The mantle also affects the long-term stability of the crust. In regions where the mantle is unusually hot or buoyant, the crust can become thinner and more stretched, creating rift zones and basins. In contrast, cooler, denser parts of the mantle can pull down on the crust, contributing to the sinking of oceanic plates into subduction zones. Even the continents themselves are influenced by the mantle's slow rise and fall. As mantle currents shift, they can lift entire landmasses or allow them to sink. This vertical motion, called dynamic topography, changes sea levels, alters drainage patterns, and shapes the evolution of coastlines over tens of millions of years. So while the mantle lies hidden beneath hundreds of miles of solid rock, its influence is everywhere, in the shape of the land, the placement of volcanoes, the patterns of earthquakes, and the slow rearrangement of continents across the face of the planet. It is the deep, molten heart of Earth's surface story. As we leave the mantle behind and descend even deeper into the planet, we enter a realm of staggering extremes, a world of crushing pressure, unimaginable heat, and metals that behave in ways no surface material ever could. This is Earth's core, the fiery heart of the planet, hidden more than 3,000 miles beneath your feet. Though no human instrument has ever reached it, scientists are confident about what lies below because of the way seismic waves move through the planet during earthquakes. These vibrations act like sonar, revealing not only the shape and depth of the core, but also its unique internal structure. And what they reveal is extraordinary. The core is made primarily of iron, with smaller amounts of nickel and traces of lighter elements like sulfur, oxygen, or silicon. These elements are extraordinarily dense, and under the extreme pressures of the deep Earth, they form the heaviest part of the planet. The core contains roughly 1/3 of Earth's total mass, despite taking up only about 1/6 of its volume. When the Earth first formed, it was entirely molten. Over time, heavier materials like iron and nickel sank to the center, while lighter materials floated toward the surface. This process, called planetary differentiation, created the layered structure we have today, with the core at the center, wrapped in the mantle, all beneath the crust. The core has remained ever since, an ancient remnant of Earth's earliest moments, slowly cooling and evolving beneath layers of rock. But the core itself is not a single uniform body. It is made of two distinct layers, separated not by composition, but by state of matter. The outer core, roughly 400 miles thick, is liquid. It flows like a molten ocean of metal, churning and swirling due to the heat rising from the deeper Earth. Beneath this liquid layer lies the inner core, a solid sphere about 760 miles in radius, roughly the size of the Moon, where the pressure is so intense that iron remains solid despite temperatures that may exceed 10,000 degrees Fahrenheit. This difference, liquid outside, solid inside, is one of the most remarkable features of Earth's interior. The outer core behaves more like a fluid, with its currents and eddies playing a vital role in generating Earth's magnetic field. The inner core, by contrast, is rigid and dense, crystallizing slowly over time as the Earth continues to cool. The boundary between these two layers is sharply defined. Seismic waves react very differently when they pass from liquid into solid, or vice versa. S waves, for instance, cannot travel through liquids, so they disappear in the outer core. But P waves continue through, bending and changing speed as they move through materials of differing densities. By carefully studying these changes, geophysicists have mapped the precise edges of the core and confirmed its dual structure. Though sealed away beneath thousands of miles of solid rock, the core is not separate from the world above. It plays a vital role in many aspects of Earth's behavior, especially in protecting life on the surface, a story we'll continue to explore. The deeper we go, the more extreme the conditions become. At the very center of the Earth, more than 6,000 kilometers beneath the surface, the environment is unlike anything else on the planet. Here, the temperature is estimated to be as high as 10,000 degrees Fahrenheit, hotter than the surface of the Sun. And yet, the pressure is so immense, over 3.5 million times greater than atmospheric pressure at sea level, that even metal behaves in unfamiliar ways. In this environment, iron crystallizes into solid form despite the searing heat. At the center, atoms are packed so tightly together that the structure of the inner core is thought to be mostly solid iron, with small amounts of nickel and possibly other light elements. The outer core, slightly cooler but still ferociously hot, remains liquid, a churning ocean of molten metal surrounding the solid heart within. The pressure is so intense that if you could somehow hold a piece of the inner core in your hand at the surface, it would instantly vaporize. The materials that exist at this depth can only remain stable under extreme confinement. And it is precisely these unusual conditions, this balance between heat, pressure, and flow, that make the core so important to life above. Because the outer core is liquid, and because it moves, it acts like a dynamo, a natural generator of electricity and magnetism. As molten iron and nickel swirl around the solid inner core, their motion gives rise to a vast, invisible force field that extends far into space. This is the geodynamo, the process by which Earth's magnetic field is created and sustained. The basic principle is this: moving electric charges generate magnetic fields. In the core, the iron-rich fluid is an excellent electrical conductor. As it moves, driven by heat and the planet's slow rotation, it sets up circular currents. These currents, in turn, generate magnetic fields. Through a complex feedback process, these magnetic fields organize into a coherent planet-scale field that surrounds the Earth in a protective bubble known as the magnetosphere. This magnetic field is not static. It pulsates, drifts, and even reverses over time. Geological records preserved in rocks show that Earth's magnetic poles have flipped many times in the past, sometimes every few 100,000 years, sometimes after longer gaps. These reversals are natural, and though their exact triggers are still studied, they are believed to originate in fluctuations within the flow of the outer core. What makes the magnetic field so vital is not just its existence, but its role in shielding life. Without it, charged particles from the sun, the solar wind, would strike Earth's atmosphere directly, gradually stripping it away. On Mars, where the magnetic field is weak or absent, this process has left the planet dry and airless. But on Earth, the magnetosphere deflects most of these particles, protecting both the atmosphere and the organisms that depend on it. High-energy particles are funneled along magnetic field lines toward the poles, where they interact with molecules in the upper atmosphere and create the glowing curtains of light we call the auroras, the northern and chaos, southern lights. These glowing waves are not just beautiful, they are visible reminders of the deep, hidden forces churning thousands of miles beneath our feet. So in a very real way, the motion of molten metal in Earth's outer core is what makes life on the surface possible. It is a silent, unseen process, but one that connects the heart of the planet to the sky above. The magnetic field that surrounds our planet is more than just a curious phenomenon. It is a vital shield, one that has protected Earth for billions of years. Without it, the surface of our world would be exposed to a continuous barrage of solar radiation, cosmic particles, and the slow stripping of our atmosphere into space. It is the silent guardian of life, generated deep within the planet, yet felt even at the edge of space. The solar wind, a constant stream of charged particles ejected from the sun, flows outward in all directions. When it reaches Earth, it encounters the magnetosphere, which deflects most of these particles around the planet, like water flowing around a stone. Without this shield, the energy from the sun would gradually erode our atmosphere, just as it has on Mars and Mercury, planets with either no magnetic field or one too weak to hold back the solar wind. More importantly, the magnetic field protects the genetic stability of life. High-energy radiation can damage DNA and other cellular components, increasing mutation rates and threatening the survival of delicate ecosystems. Thanks to the magnetosphere, much of this radiation is blocked or diverted toward the poles, where it causes no harm. When solar particles do enter the atmosphere, they interact with molecules high above the surface, creating the shimmering curtains of green, blue, and violet, known as the auroras. These auroras are not just beautiful, they are visual evidence of the magnetic field at work, the only sign to the naked eye of the colossal engine turning at the center of the Earth. And yet, for something so important, the core remains profoundly out of reach. No probe has ever visited it. No drill has pierced even the outer layers of the mantle, let alone the core. So how do we know what's down there? The answer lies in a combination of indirect methods, especially seismology and geomagnetism, two of the most powerful tools in Earth science. Seismology is the study of vibrations within the Earth, especially those generated by earthquakes. When a quake occurs, it sends out waves that travel through the planet's interior. These waves move at different speeds depending on the type of material they pass through, and they bend or reflect when they encounter boundaries between layers. By studying how seismic waves behave as they travel through the Earth, scientists can reconstruct the internal structure of the planet, including the size, density, and state of the core. Two main types of seismic waves are used: P waves, which can travel through both solids and liquids, and swaves, which only move through solids. When swaves fail to appear on the far side of the planet after an earthquake, it reveals the presence of a liquid layer, in this case, the outer core. P waves, meanwhile, slow down and bend as they pass through the liquid outer core, then speed up again through the solid inner core. These changes provide precise measurements of the core's depth, shape, and composition. Geomagnetism, the study of Earth's magnetic field, offers another window into the core's behavior. By tracking changes in the field over time, scientists can model the flow of molten metal in the outer core. Fluctuations in magnetic strength and direction reveal how the core's currents are shifting and how the geodynamo is evolving. Satellite missions, such as ESA's Swarm constellation, continuously monitor the magnetic field, capturing its small variations with extraordinary precision. These techniques, combined with high-pressure laboratory experiments and simulations of core behavior, give us a surprisingly detailed understanding of a place we cannot touch, a world of metal, heat, and motion, sealed away at the center of the Earth. For all we've learned about the Earth's core, it remains one of the most mysterious regions of our planet, a place we know only through vibrations and magnetic whispers. Many of its behaviors are still not fully understood, and each discovery seems to open a new layer of uncertainty. One such puzzle is the rotation of the inner core. Seismic data suggests that the solid inner core may rotate slightly faster or slower than the rest of the planet, a phenomenon known as differential rotation. Some studies show it speeding up or slowing down in cycles that may be tied to changes in Earth's magnetic field. But the exact cause, rate, and effects of this motion remain debated. Even the age and formation of the inner core is a matter of scientific inquiry. While the Earth itself is over 4.5 billion years old, the solid inner core may have formed much more recently, perhaps only 1 to 1.5 billion years ago, as the planet slowly cooled enough for iron to crystallize at the center. This late formation could explain the strengthening of the magnetic field in Earth's more recent geologic past. Another mystery lies in the asymmetry of the inner core. Seismic waves travel at slightly different speeds depending on the direction they pass through it, hinting that one side of the core may be cooling or growing faster than the other. Some researchers propose that heat may be escaping unevenly, or that compositional differences exist between the eastern and western hemispheres of the core, but so far, no model fully explains the observed data. There is even evidence that layers exist within the inner core itself, a solid inner core with different crystal orientation or structural properties. This would suggest that the deepest part of the Earth has its own history and internal complexity, a kind of planet within a planet, with dynamics still unfolding. And so, as we prepare to leave the core behind and journey outward once again, we do so with a sense of humility. For all our tools and models, the heart of the Earth remains largely unknown, a realm of fire and metal, spinning in silence far beneath our feet. To understand the engine that drives Earth's internal processes, the drifting of continents, the rise of volcanoes, the subtle motion of the crust, we must turn our attention to a single force: heat. Heat is what keeps the mantle moving, what fuels the geodynamo in the core, and what powers the ongoing renewal of the planet's surface. But where does this energy come from? There are two primary sources of heat inside the Earth. The first is primordial heat, energy left over from the violent birth of the planet. Over 4.5 billion years ago, the young Earth formed through collisions, mergers, and gravitational compression of smaller bodies in the early solar system. These impacts released immense amounts of energy, heating the growing planet until it was completely molten. As the planet cooled and solidified, much of that heat was retained in the deep interior. This primordial heat has been slowly leaking out ever since, flowing through the mantle and crust and radiating into space. But it hasn't been enough to keep the Earth geologically active for billions of years on its own. The second major source of heat is radioactive decay, a steady, long-term energy source that continues to warm the planet from within. Certain isotopes are naturally unstable. As they decay into more stable forms, they release energy in the form of heat. These isotopes are found primarily in the crust and upper mantle, and their decay provides a continuous supply of thermal energy. This heat drives mantle convection, supports volcanic activity, and sustains the magnetic field by powering convection in the outer core. Together, these two sources, the fading embers of a violent origin and the steady burn of radioactive elements, keep the Earth alive beneath its rocky surface. Heat is always on the move. In every part of the Earth's interior, from the crust to the core, energy flows from warmer regions to cooler ones. And while the sources of heat inside the Earth are important, it's the movement of that heat that shapes the planet. Scientists identify three main ways that heat moves through Earth's interior: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact. It's the same process that warms the handle of a metal spoon placed in hot soup. In Earth's interior, conduction allows heat to flow from one layer to the next where material is solid and relatively still. For example, heat conducts slowly from the hot mantle into the cooler base of the crust. Because rocks are not particularly good conductors, this process is slow, but it's steady, and it allows heat to gradually rise through static layers. Convection, on the other hand, is the movement of heat through the motion of fluid, or in Earth's case, solid rock, that flows over long periods of time. As mantle rock is heated from below, it becomes slightly less dense and rises toward the surface. Cooler, denser rock then sinks downward, creating circular currents that carry heat upward and cooler material back down. This is the dominant heat transfer process in the mantle and outer core. Radiation is the transfer of energy through electromagnetic waves. It's how heat from the sun reaches the Earth. Inside the Earth, radiation plays a smaller role, but it does occur within the core and in tiny amounts at the atomic scale. Most of the heat transfer within the Earth, however, happens through conduction and convection, especially in the deep mantle, where these processes power nearly every aspect of geologic change. It is convection, more than any other mechanism, that drives the great movements of Earth's surface. The heat rising from the deep interior, whether from radioactive decay or primordial origins, causes mantle rock to circulate in enormous, looping currents. These mantle convection cells are slow but incredibly powerful, moving material at rates of just a few inches per year. And because the tectonic plates float atop the upper mantle, they are carried along by these same currents. Where mantle material rises, it creates divergent boundaries, regions where tectonic plates are pushed apart. Mid-ocean ridges are one example. Long undersea mountain chains where magma from the mantle wells up and forms new crust. As this new crust spreads outward, older crust is pushed away from the ridge, causing the plates to drift slowly in opposite directions. Where mantle material sinks, usually as a result of a descending, cooler plate, convergent boundaries form. Here, one plate is forced beneath another and pulled down into the mantle in a process known as subduction. This sinking plate carries with it water, sediments, and crustal material, which melt and fuel volcanic activity above. These subduction zones are the sites of deep ocean trenches, explosive volcanoes, and powerful earthquakes, all driven by the slow churning of the mantle beneath. Even so-called stable continental interiors are not immune to this movement. The rising and sinking of mantle material can cause whole regions to swell or sag over geologic time, lifting plateaus, opening rift valleys, or altering drainage patterns. The connection is profound. Heat becomes motion, and motion becomes the sculptor of the planet's surface. Every mountain, every basin, every shifting fault line is a response to the silent, steady rise of thermal energy from within. And though we may walk the surface in stillness, the deep earth is always moving. Deep within the earth, heat does more than move. It builds pressure, melts rock, and fuels some of the most dramatic processes we see on the surface. One of the most visible expressions of internal heat is volcanic activity, where molten rock formed in the mantle or lower crust makes its way to the surface and erupts as lava, ash, and gas. Volcanoes exist because Earth's interior is hot enough to partially melt rock. In subduction zones, water and minerals carried downward by a sinking plate lower the melting point of surrounding rock, allowing magma to form. In rift zones, where plates are pulled apart, the pressure drops rapidly, also causing rock to melt. And above mantle plumes, rising columns of hot material create hotspots, fixed points where magma pierces through the crust over and over again. When magma rises, it collects in chambers near the surface. Pressure builds as gases within the magma expand, until the rock above can no longer contain it. The result can be a slow ooze of lava or a violent explosion depending on the magma's temperature, composition, and gas content. Every volcanic eruption is the final stage of a long journey that began with heat rising in the deep earth. In quieter settings, that same heat powers geothermal activity. In places like Iceland, New Zealand, and Yellowstone National Park, groundwater seeps deep underground, where it is heated by underlying magma or warm rock. This superheated water then rises back to the surface, emerging as geysers, hot springs, steam vents, or boiling mud pools. Though these features may seem gentle compared to volcanoes, they are fed by the same forces, a continuous, low-level release of Earth's inner heat. Geothermal energy is one of the few ways humans have tapped directly into this internal warmth. In some regions, wells are drilled to access hot water or steam, which can be used to heat buildings or generate electricity. This energy is clean, sustainable, and nearly limitless, as long as the planet continues to cool from within. But that cooling is happening, slowly and steadily. Over geologic time, Earth has been losing heat to space. The surface radiates thermal energy outward, and heat from the interior conducts through the crust, rising into the oceans and atmosphere. This flow of heat is incredibly gradual, only a few hundredths of a watt per square meter on average, but across the entire surface of the Earth, it adds up to a significant loss. The planet's energy balance is complex. While it still receives energy from radioactive decay and retains some primordial heat, it has been cooling since its formation. 4 billion years ago, the Earth was far more geologically active, with more frequent and massive volcanic eruptions, thinner crust, and a hotter mantle. Plate tectonics likely operated differently then, and the core's behavior may have been more chaotic. As Earth cools, changes continue. The inner core is slowly growing as more iron crystallizes from the liquid outer core. This process releases additional heat and light elements into the outer core, helping to sustain the geodynamo, for now. But over billions of years, as radioactive elements decay and the core loses energy, the planet will become geologically quieter. The magnetic field may weaken. The mantle may slow. The plates may one day grind to a halt. That time is unimaginably far in the future. For now, Earth remains a living planet, its internal heat flowing outward, powering motion, change, and life itself. Though it lies hidden deep within the planet, Earth's internal heat has effects that stretch far beyond the mantle and crust. One of its most far-reaching influences is on the magnetic field, which is not constant or fixed, but dynamic and ever-changing. These magnetic fluctuations, from subtle drifts to full reversals, are ultimately powered by heat flowing through the core. The movement of molten iron in the outer core, driven by convection and influenced by Earth's rotation, is what generates the magnetic field. But this movement is shaped by how heat escapes from the core into the mantle above. When heat flows efficiently out of the core, for example, in areas where the lower mantle is cooler and more stable, convection in the outer core becomes stronger and more organized. This strengthens the magnetic field and increases its stability. But in regions where the mantle is hotter or more sluggish, the flow of heat from the core can slow down. When that happens, convection in the outer core becomes less vigorous, and the magnetic field can weaken or become more chaotic. These regional variations help explain why the magnetic field isn't uniform across the planet, why it has patches of intense strength in some places and weaker zones in others. Over longer timescales, the field undergoes geomagnetic reversals, where the north and south magnetic poles switch places. These reversals happen irregularly, roughly every few 100,000 years, and appear to be linked to changes in the flow patterns of the outer core. Though the precise mechanisms remain uncertain, many scientists believe that shifts in the thermal balance between the core and the mantle may play a key role, subtly altering the patterns of fluid motion that sustain the prow. Geodynamo. Even without full reversals, the magnetic field is constantly drifting. The magnetic North Pole, for example, is moving across the Arctic at a rate of dozens of kilometers per year, a reflection of subtle changes in the deep Earth that slowly ripple outward to the surface. In this way, Earth's heat flow doesn't just shape rock and landscape. It shapes invisible forces as well, planetary-scale systems that protect life, guide migratory animals, and interact with the space environment. But perhaps the most familiar expression of Earth's internal heat is in its surface geology, in the relationship between heat and the landscapes we know. Volcanoes, mountain ranges, earthquakes, rift valleys, and ocean trenches are all surface manifestations of deeper thermal processes. When the mantle convects, it moves the tectonic plates. When plates collide or diverge, the crust responds with deformation, uplift, or volcanic eruption. And when magma rises toward the surface, it brings heat, pressure, and new material into the crust, altering ecosystems, building new land, and, at times, reshaping entire regions. Even more subtle changes, like the slow warping of continents, the rise and fall of coastlines, or the sagging of land beneath glaciers, are often tied to variations in heat flow and mantle movement. Over millions of years, regions rise or sink in response to the mantle's shifting currents, which in turn are driven by temperature differences deep below. In a sense, the Earth's surface is like a skin, one that flexes, breathes, and moves in response to internal forces. It may feel still beneath our feet, but it is anything but static. The warmth beneath us is constantly working, lifting one region, lowering another, cracking the crust, and fusing it back together in new forms. So while we may never feel the heat of the deep Earth directly, we live in its presence every day. It is in the shape of mountains, the path of rivers, the tremble of the ground, and the quiet breath of steam from a spring. The planet's inner warmth continues to power its story, above and below. Although most of Earth's inner workings happen far beneath the surface, their effects are often felt most vividly in sudden, dramatic events above ground. Two of the clearest and most powerful expressions of deep Earth processes are earthquakes and volcanoes, natural phenomena that begin with slow motion deep underground, but unfold at the surface in seconds or minutes. They are the loudest whispers of the planet's inner voice. Earthquakes occur when stress builds up in the Earth's crust and is suddenly released. This stress comes from the slow movement of tectonic plates, the rigid slabs of crust and upper mantle that glide across the surface of the planet. As plates grind past one another, collide, or pull apart, they don't move smoothly. Instead, friction holds them in place until the pressure becomes too great. Then, in a sudden lurch, the rock breaks or shifts along a fault line, sending vibrations through the surrounding material. This release of energy travels outward in all directions in the form of seismic waves. The point underground where the rupture begins is called the focus, and the location directly above it on the surface is known as the epicenter. Though the movement begins deep below, the shaking is felt on the surface, sometimes gently, sometimes violently, depending on the magnitude of the event and the type of material the waves travel through. There are two primary types of seismic waves generated by earthquakes: PWs and swaves. PWEES, or primary waves, are compression waves. They move quickly through solid rock, liquid, and gas, compressing and expanding the material they pass through, much like sound waves in air. Waves are the fastest seismic waves and typically arrive first at seismic monitoring stations. Swaves, or secondary waves, travel more slowly. They move material side to side or up and down like the ripples on a shaken rope. Swaves can only move through solids, not through liquids, a fact that has provided critical insight into the structure of Earth's interior. For example, when swaves from deep earthquakes fail to pass through certain layers, scientists know those regions must be liquid, such as the outer core. By analyzing the arrival times and behavior of these waves at different monitoring stations around the world, scientists can map the shape and composition of the Earth's interior. The way seismic waves bend, reflect, or disappear tells us where boundaries exist between crust and mantle, between mantle and core, and even helps reveal the temperatures and densities of those layers. But beyond their role in science, seismic waves are also a deeply human experience. The trembling of the ground, the shifting of structures, the quiet moment before an aftershock, all are reminders that the earth beneath us is alive and that its surface is connected to a deeper story unfolding miles below. In this wave of the journey, we'll explore how these deep movements shape the land through earthquakes and volcanic eruptions, and how studying their patterns helps us better understand the powerful, shifting forces inside our planet. If earthquakes are sudden releases of built-up pressure, then volcanoes are gradual, often spectacular expressions of deeper heat. They form where molten rock, or magma, rises through the crust, eventually reaching the surface as lava, ash, and gas. Every volcano on Earth is connected to a process that begins miles underground, sometimes in the upper mantle, sometimes in the lower crust, where intense heat melts solid rock and sets it in motion. Volcanoes are found in several key geologic settings, each shaped by a different interaction between tectonic plates. Along divergent boundaries, where plates move apart, magma rises to fill the gap. This happens at mid-ocean ridges like the Mid-Atlantic Ridge, where new oceanic crust is constantly being formed by steady volcanic eruptions beneath the sea. These underwater volcanoes rarely make headlines, but they are among the most productive on the planet. At convergent boundaries where one plate is subducted beneath another, magma forms as the sinking plate carries water and minerals down into the mantle. These materials lower the melting point of the surrounding rock, causing it to partially melt and rise toward the surface. The result is a line of volcanoes, often explosive, steep-sided, and tall, like the ones that ring the Pacific Ocean in the Ring of Fire. Volcanoes can also form above mantle plumes, where columns of hot material rise from deep within the mantle and break through the crust. These so-called hotspots are responsible for island chains like Hawaii and the Galapagos, where one volcanic island after another is built as the tectonic plate moves slowly over the stationary plume. The style of eruption varies depending on the composition and temperature of the magma. Basaltic magma, which is hot and low in silica, flows easily and produces relatively gentle eruptions. These eruptions create shield volcanoes, wide, gently sloping landforms like Mauna Loa in Hawaii. The lava spreads out in thin sheets, traveling long distances before cooling. By contrast, andesitic and rhyolitic magmas are cooler and contain more silica, making them thicker and more viscous. This kind of magma traps more gas, leading to pressure buildup within the magma chamber. When the pressure becomes too great, it can trigger a violent eruption, one that blasts ash, rock, and gas high into the sky. These eruptions create stratovolcanoes, such as Mount St. Helens, Mount Fuji, or Mount Vesuvius. Their slopes are steeper, and their eruptions are often sudden and destructive. The journey of magma begins deep below, but it follows a complex path as it rises. In the mantle, partial melting occurs when temperature, pressure, or composition conditions shift enough to allow some rock to liquefy. This molten rock, being less dense than the surrounding solid material, begins to rise through fractures and weaknesses in the overlying rock. As magma ascends, it may pause in magma chambers, underground reservoirs that collect molten rock over time. These chambers can remain dormant for years or centuries, quietly growing in volume and pressure. When enough magma accumulates, or when a new fracture opens a path to the surface, the chamber may empty in an eruption. The type of eruption, slow or explosive, depends on how quickly the pressure builds and how easily gases can escape. Even after an eruption, magma may continue to rise, keeping the system active. Some volcanoes erupt continuously, with slow lava flows and steady gas release. Others remain silent for centuries, storing potential energy until a new cycle begins. From the moment magma forms to the instant it bursts free at the surface, volcanoes are vivid, fiery reminders of the immense heat moving through Earth's interior. Earthquakes and volcanoes may seem like separate phenomena, one driven by pressure, the other by heat, but in reality, they are deeply connected. Both arise from the movement of tectonic plates, and both are most commonly found along plate boundaries, where the crust is in constant motion. At divergent boundaries, plates pull apart. As they do, magma rises to fill the gap, forming new crust in a continuous, slow process. These spreading centers are often quiet but persistent, producing gentle earthquakes and underwater volcanic activity that creates vast oceanic ridges. Although these quakes are usually small, they form a near-constant background of motion across the sea floor. At convergent boundaries, one plate sinks beneath another in subduction zones. This process generates both powerful earthquakes and explosive volcanoes. As the subducting plate is forced downward, stress builds up along the interface where the plates grind against each other. Eventually, that stress is released as a massive earthquake, often followed by tsunamis if the rupture occurs beneath the ocean. Meanwhile, as the descending plate melts, it produces magma that rises to the surface, feeding a line of volcanoes inland from the trench. Transform boundaries, like the San Andreas Fault in California, are another major site of seismic activity. Here, plates slide past each other laterally. These boundaries do not typically produce volcanoes, but they are responsible for some of the most damaging earthquakes in human history. Because the motion is horizontal rather than vertical, the pressure accumulates in a different pattern, creating long fault lines where sudden shifts can fracture the crust. Together, these boundaries form a global system of stress and heat exchange. They are not isolated zones, but parts of a planetary mechanism that constantly reshapes the Earth's surface. And while the movement is slow, often just millimeters or centimeters per year, its effects can be sudden, immense, and profoundly transformative. The human impact of these events is far-reaching. Earthquakes can collapse buildings, rupture roads, and cut power and water supplies in seconds. Entire cities can be shaken to rubble in moments, and the aftershocks can linger for weeks. In mountainous regions, quakes can trigger landslides and avalanches. In coastal zones, undersea quakes can generate tsunamis that travel across oceans and inundate shores with devastating force. Volcanoes, too, can reshape landscapes and lives. Explosive eruptions can blanket entire regions in ash, collapse roofs, poison water supplies, and darken the skies for days or weeks. Fast-moving flows of hot gas and ash, called pyroclastic flows, can destroy everything in their path. Lava flows, while often slower, can engulf homes, forests, and farmland. And in the wake of an eruption, long-term hazards like acid rain, crop failure, and respiratory illness may persist. But not all effects are destructive. Volcanic soils are among the most fertile on Earth, enriched with minerals released from deep within the planet. Many of the world's great civilizations, from the Nile Delta to the Andes, have flourished in volcanic regions, drawn by the richness of the land despite the risk. Geothermal activity also provides clean, renewable energy in places where Earth's heat is close to the surface. In many ways, earthquakes and volcanoes remind us that the planet is alive. They are signs of an Earth that is still evolving, still shifting beneath our feet. And while they pose real danger, they are also expressions of the deep, dynamic processes that make Earth the unique and life-supporting world it is. Though earthquakes and volcanoes often strike without warning, they are not beyond study. and not entirely beyond prediction. In fact, by monitoring these events closely, scientists gain not only a better understanding of when and where hazards might occur, but also deeper insights into the structure and behavior of the planet itself. Seismic monitoring stations are now positioned around the globe, constantly listening for the slightest tremble in the Earth. These networks detect thousands of earthquakes every year, from massive ruptures to subtle micro-quakes deep beneath the surface. By analyzing the timing, strength, and pattern of seismic waves, researchers can locate faults, measure plate movement, and even map the flow of rock in the mantle. Volcanoes, too, are carefully watched. Instruments measure ground deformation, gas emissions, thermal activity, and even the tiniest seismic vibrations known as volcanic tremor. These signals can indicate that magma is rising, or that pressure is building within a chamber. By comparing present activity to past eruptions, volcanologists can sometimes issue warnings, helping communities prepare for possible events and saving lives in the process. These monitoring efforts also reveal much more than immediate hazards. Every earthquake and eruption acts like a probe into the planet's interior. Seismic waves generated by these events pass through the crust, mantle, and core, changing speed and direction based on the materials they encounter. By collecting data from many different locations, scientists can construct three-dimensional models of Earth's inner structure, revealing not just where magma rises or faults lie, but how heat flows and rock deforms in the deep Earth. In a sense, each tremor is a conversation between the surface and the interior, and by listening closely, we've begun to translate its language. Despite centuries of study and increasingly sophisticated technology, the inner Earth remains one of the greatest frontiers in science. We've mapped its broad structure, crust, mantle, outer core, inner core, but many of the most fundamental questions about its composition and behavior remain unresolved. The composition of the core, for example, is still partly a mystery. We know it is mostly iron and nickel, but the core's density is slightly lower than expected if it were pure metal. This suggests that lighter elements, perhaps sulfur, carbon, oxygen, or silicon, are mixed in, but in what proportions and why is still debated. These differences may influence how heat moves through the core, how the inner core crystallized, and even how the magnetic field is sustained over time. Another unknown lies in the growth of the inner core. As the Earth cools, iron slowly crystallizes from the outer core and adds to the inner core's solid mass. But recent seismic data suggests that this growth may be asymmetrical, faster on one side than the other. What causes this imbalance? Could heat be escaping more efficiently in certain regions of the mantle? Or might the inner core itself be slightly off-center, wobbling or rotating independently from the rest of the planet? There's also evidence of a layered structure within the inner core, perhaps an inner core with a different crystal orientation or composition. Some seismic waves pass through this central region at unexpected speeds, hinting that it may have formed under different conditions or at a different time in Earth's history. If confirmed, this would suggest the core has a much more complex history than previously thought. And then there's the question of how the magnetic field changes over time. We know it drifts, pulses, and even reverses. But why these changes happen when they do, and what they mean for the long-term stability of the geodynamo, is not fully understood. Are they caused by subtle changes in heat flow, variations in core composition, or chaotic turbulence deep in the molten metal itself? These questions aren't just academic. The behavior of the core influences everything from navigation systems to climate stability to our ability to sustain life on Earth. Understanding its mysteries is key to understanding the future of the planet. Even though we cannot travel to the Earth's core, we continue to make progress in exploring its hidden structure, not just through theory, but through tools, experiments, and direct sampling of the uppermost layers. Among the boldest of these efforts are deep drilling projects, which attempt to reach farther into the Earth than ever before. The most famous of these is the Kola Superdeep Borehole, a Soviet-era experiment that began in 1970 and eventually reached more than 7 miles down into the continental crust. Though that depth is only a fraction of the distance to the mantle, let alone the core, the Kola project revealed a wealth of surprises. It discovered high-temperature rock far earlier than expected, found water trapped in mineral structures deep underground, and encountered unexpected variations in seismic velocity, suggesting that the crust is more fractured and variable than models had predicted. Today, other ambitious projects continue this work. Japan's Chikyu drilling vessel is capable of boring deep into the oceanic crust and has helped gather seismic and thermal data from active fault zones. In Iceland, deep wells have tapped directly into geothermal systems driven by magma, allowing scientists to study rock at the edge of partial melting. These boreholes give us real-world samples of materials that were once miles below the surface, pieces of Earth's interior brought into the light. But the most detailed images of the deep Earth don't come from drilling. They come from listening. Seismic tomography, the process of creating three-dimensional maps of Earth's interior using earthquake waves, has revolutionized our understanding of the planet's internal structure. By collecting data from thousands of seismic stations worldwide and modeling how waves bend, reflect, and slow down, scientists can create dynamic, layered images of features deep below the surface. These images have revealed mantle plumes, subducting slabs, and vast, mysterious regions near the core mantle boundary called large low-shear velocity provinces. These LLSVP are thought to be chemically distinct from the surrounding mantle, massive, possibly ancient blobs of material that may influence mantle convection, hotspot formation, and even the planet's rotation. Their origin is still debated. Some believe they are remnants of early planetary collisions. Others think they may have formed as subducted crust accumulated at the base of the mantle over billions of years. And as we build clearer pictures of Earth's interior, we naturally begin to ask, how does our planet compare to others? Thanks to missions to the Moon, Mars, and beyond, we've learned that other rocky worlds also have layered interiors, crust, mantle, and core, but the details vary widely. The Moon, for instance, has a small, partially molten core, a thick mantle, and a crust that cooled quickly. Its magnetic field is weak and ancient, likely extinguished long ago when its core stopped convecting. Mars has an iron-rich core that may still be partly liquid, but it no longer supports a global magnetic field. Its mantle appears to have cooled faster than Earth's, perhaps because Mars is smaller and loses heat more quickly. The lack of active plate tectonics on Mars has left its surface scarred but stable, with giant volcanoes like Olympus Mons that have sat quiet for millions of years. Even Mercury, despite its small size, has a surprisingly large iron core, making up more than half the planet's volume. And Venus, similar in size to Earth, shows signs of internal heat, but lacks clear evidence of plate tectonics, suggesting it may lose heat differently, perhaps through episodic surface overturns rather than steady BA. Motion. These comparisons remind us that Earth's interior isn't just unique. It may also be essential to why our planet remains active, habitable, and magnetic. The way heat moves through Earth, the way rock flows and plates shift, and the way our core churns in silence, these are not universal traits. They are part of what makes Earth, Earth. It might seem surprising that something as distant as the Earth's deep interior could have any influence over something as delicate as the climate. After all, weather happens in the atmosphere, driven by sunlight, ocean currents, and air pressure. But over long spans of time, thousands to millions of years, processes deep beneath our feet have helped regulate the planet's climate in profound and essential ways. One of the most important connections lies in the carbon cycle. Carbon moves between Earth's interior, oceans, atmosphere, and living organisms. But a significant portion of that exchange is driven by plate tectonics and volcanic activity. When volcanoes erupt, they release carbon dioxide, a greenhouse gas, into the atmosphere. This may sound dangerous, and in large, sudden amounts, it can be, but over geologic timescales, this process is balanced by carbon removal through chemical weathering and sediment burial. Here's how it works. As carbon dioxide from volcanic eruptions accumulates in the atmosphere, it reacts with rainwater to form a weak acid that breaks down silicate rocks on land. This weathering process draws CO2 out of the air and carries it into rivers and oceans, where it becomes trapped in marine sediments, often as limestone. Over millions of years, these sediments are buried and, through subduction, returned to the mantle, where heat eventually drives the carbon back to the surface through new volcanic eruptions. This natural thermostat, driven by the movement of tectonic plates and the recycling of crustal material, helps to stabilize Earth's climate over time. When volcanic activity increases, more CO2 warms the planet. When mountain ranges form and expose more rock to weathering, more CO2 is pulled from the air. The balance shifts slowly, but it has allowed Earth to avoid both runaway greenhouse conditions and deep freezes like those that have affected some other planets. Beyond carbon, the internal engine of the Earth also influences climate through the creation of continents and ocean basins, which in turn affect ocean currents and wind patterns. The shifting of land masses alters the shape of the oceans, changes how heat is distributed across the planet, and can trigger ice ages or warm periods depending on the arrangement. Even small changes in elevation caused by mantle, upwelling, or crustal thinning can shift regional climates. All of this underscores a single, humbling truth. The surface of the Earth is not separate from its interior. The visible world, with its forests, rivers, and weather, is intertwined with invisible forces far below. Understanding climate in its full context means understanding the long rhythms of tectonic and volcanic activity that unfold over tens of millions of years. And yet, much remains unknown. That is why scientists continue to develop new tools and techniques, hoping to peer deeper into the planet and to watch its internal workings in finer and more immediate detail. In the coming decades, advances in computing power will allow geophysicists to simulate the core, mantle, and crust with unprecedented resolution. These models will help test theories about mantle plumes, core crystallization, and tectonic evolution, offering virtual laboratories for ideas that cannot be tested directly. Next-generation seismic networks, including dense local arrays and satellite-linked instruments, will provide higher-quality data on earthquakes, allowing scientists to trace the paths of seismic waves with more precision than ever before. These waves will continue to reveal the shape and motion of deep Earth structures, even those thousands of kilometers down. And quantum sensors, a technology now in early development, may one day detect subtle shifts in gravity, magnetism, or heat flow, offering a new way to watch the Earth's heartbeat in real time. With each advance, the boundary between the known and the unknown recedes. What was once imagined, molten seas, drifting plates, spinning metal harps, becomes visible, measurable, and real. For most of human history, the interior of the Earth was a place of imagination, a realm of myth, metaphor, and mystery. Ancient stories described it as a kingdom of fire or the underworld of spirits. Even in the early days of science, the idea of reaching the center of the Earth was more fantasy than fact, popularized in fiction, but unreachable in reality. Today, we know more. We've mapped the planet's layers, tracked seismic waves through its depths, and simulated its internal dynamics with supercomputers. And yet, in many ways, the deep Earth remains as unseen and unknowable as ever, a place we study from a distance, using echoes and traces to piece together a story we can never directly observe. There is something profoundly humbling about this kind of knowledge, the kind that is inferred, never touched. It reminds us that the Earth is not just a surface we walk upon, but a vast, complex, evolving system. Every tremor, every volcano, every shift in the magnetic field is a signal from a hidden world, one that has been turning beneath us since before life began. And so, to explore Earth's interior is to engage with a kind of quiet reverence. We are listening to a planet that speaks in slow pulses and buried movements, in flows of heat and waves of pressure. Its voice is subtle but persistent, a deep rhythm that underlies every forest, every ocean, every breath we take. There is also a certain beauty in not being able to see it directly. Unlike the stars or the sea, which we can observe with our eyes, the Earth's interior must be understood indirectly. It requires trust in data, in patterns, in the slow accumulation of knowledge. It challenges us to think in deep time and deep space, not just across miles, but across millions of years. This unseen world is full of paradoxes. It is solid, yet flowing, remote, yet connected to our lives. It creates destruction, earthquakes, eruptions, mass extinctions, yet also enables creation, continents, mountains, soil, and life. It hides its secrets, but leaves fingerprints everywhere. And perhaps that is what makes it so endlessly fascinating. We live every day on the surface of a living, breathing planet, yet we often forget that most of it is hidden. More than 90% of Earth's mass lies below the crust, inaccessible, mysterious, and constantly in motion. It is not just the foundation of our world. It is the engine, the archive, the memory of everything the planet has ever been. So as we reflect on our journey so far, from the familiar crust to the shifting mantle, down into the molten outer core and solid inner core, we can pause and feel a kind of quiet awe. There is a vast, dynamic world beneath our feet, older than any civilization, deeper than any ocean, and more enduring than any mountain. To study it is to learn patience. To imagine it is to touch wonder. And though we may never reach its center, the Earth continues to speak to us, in tremors, in flows, in fields. We only have to listen. We've traveled far tonight, not across the surface of the world, but deep within it. From the soil beneath your feet to the fiery heart of the planet, we've drifted gently through stone, pressure, and heat, following the invisible threads that hold the Earth together. We began at the crust, where life unfolds and mountains rise, a fragile, drifting shell shaped by movement below. Then we slipped into the mantle, a realm of slow-flowing rock and quiet strength, where heat becomes motion and motion shapes the continents. Deeper still, we entered the core, molten, immense, and hidden, the engine of Earth's magnetic shield and the silent guardian of life above. Along the way, we listened to the tremble of seismic waves, watched magma rise to form new land, and glimpsed the long rhythms of planetary cooling stretching across billions of years. We wondered at the boundaries we cannot cross, and the mysteries that still remain, the strange rotation of the inner core, the deep chemistry of molten metal, and the slow drift of magnetic poles. And now, at the end of our descent, we return to the surface, not as we left it, but with new eyes. Beneath every quiet landscape, every ridge and valley, there is motion. Beneath every tremor, every island, every fault line, there is heat. And beneath all of us, every moment of every day, the Earth is alive, shifting, turning, changing in silence. So, if you're drifting into sleep now, let yourself rest. Let your breath slow and your thoughts settle. There's no need to remember every layer, every term, every detail. The science will still be here, waiting gently when you return. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.